Good morning, everyone. Today I will be presenting on the topic of the concept of stationarity and statistical independence in random process. We will explore the different types of stationarity from first order to strict sense and understand how they help us analyze random signals in communication systems. I'm the My name is J.B. Ganesh from Department of Electronic and Communication Engineering in the VVIT College, and I have to discussing about introduction of random process definition. Let's begin with the basics. A random process is simply a collection of random variables that change over time, and examples include background noise in communication channels, temperature fluctuations, or even stock market prices. Where they are in random in nature, they will go in up and down sequences. This waveforms is examples for random processes. To analyze this process, we study the statistical characteristics, mainly the mean, autocorrection, and statistical properties. Next slide is concept of stationarity. By the visual, we can see that graph comparing stationarity and non-stationarity mean where the signal and the spectrum, where signal is the time domain and spectrum is the frequency domain. Stationarity means the statistical properties of process do not change with time. If the mean, variance and correlation remain constant, we call it stationarity. This assumption simplifies mathematically modeling and helps in analyzing systems like noise filters or amplifiers. For example, a steady white noise signal has a constant average power and is considered stationary. Where it's non-stationary, a steady white noise signal has not a constant average power and is considered as a non-stationarity. By next slide, the mathematical conditions for stationarity. By the figure, we can see that no autocorrelation and it is in the random in nature. There are no waveforms in, but autocorrelation, it is considered as a waveform in a constant mean and variance. For a process x of t, constant mean is equal to expectation of x of t is equal to constant variance of x of t is equal to expectation x square of t minus expectation x square of t is equal to constant. Autocorrelation depends only on lag, where autocorrelation um, denoted as r of x by the two random variables at r of x of t1 comma t2 is equal to r of x of tau, where tau is equal to t2 minus t1, where t2 and t1 are the time constants. Consequence, statistically descriptors becomes function of tau, enabling Fourier techniques of power spectral density. Statically independence, it has a definition and example I have discussing about, where two samples like x of t1 and x of t2, where they are in two independent probability distributions. We can see the diagram. The There are three lines like joint, marginal, and conditional, where they are called joint, marginal, conditional are the process p of x of t1 comma x of t2 is equal to p of x of t1 into p of x2 x t2. It is multiplied because of the independent of two random variables. And statistically independent, independence implies no probabilistic coupling stronger than autocorrelated, where example independent white noises samples from an ideal RNG. We can see that joint PDF factorized into product of marginal. when independent statistically two samples are in multiplied. The next is first order stationarity definition. A first order stationary process means that it first order probability distribution or a PDF or a cumulative distribution function is invariant, or it does not change or over time or under time. This shift is fx of x comma t is equal to fx of x for all time period time t. Implications mean mu of t is constant, variance stable over time, where in the previous one both mean and variance are the constant, but this time mean only constant and variance is stable over time. Example, thermal noises where instantaneously amplitude distributions remains the same across the time instance. And next is second order stationarity. There, second order stationarity, and the topic calls wide sense stationarity also included. When both the mean and autocorrelation remains constant over time, the process is called second order stationarity or a wide sense stationarity. This property allows us to study the power of and frequency behavior of signals easily. Most real world signals like Gaussian noise are modeled as WSS for simplicity system analysis. For wide sense stationarity, WSS called in WSS two conditions are hold. The mean is constant or mu of expectation of x of t is equal to mu. The autocorrelation depends only on time difference. For the autocorrelation, we can derive the power spectrum density like using power spectral density by the power Fourier transform. We can derive f is equal to f of r of x and tau. And next is nth order stationarity. In nth order stationarity, every joint distribution of n samples is invariant. A process of nth order stationarity if its joint probability distribution for any n samples remains the same even after a time shift. In the mathematical form, f of x of x1 comma x2 comma or xn comma t1 comma c comma tn plus c and so on is equal to f of x comma x1 comma xn and so on by the infinity. As n grows, constant tighten and n tends to infinity gives strict sense stationarity. Example, Gaussian processes are fully characterized by the first two moments. So WSS often implies SS triple S is if Gaussian and Gaussian process that satisfies all order of stationarity. Next we are discussing about SSS, strict sense stationarity. Finally, strict sense stationarity means that all statistical properties of an order remain unchanged with time shifts. This implies the process looks statistically identical no matter when we observe it. It has constant mean, variance, and autocorrelation depending only on tau or time period. Through strict sense stationarity is ideal and rarely seen in practice, informs the theoretical foundation for modeling random process by the comparison of stationarity types. The comparison and practical test and takeaways in first order and second order and nth order. Here's a quick comparison by the figures. First order constant means, second order constant mean and correlation depending only on LS, nth order constant endpoint distribution. And strict distance, all distributions are constant with time shifts. For example, steady noise in first order stationarity, while Gaussian noise can be considered WSS or even SSS in theory. And next is summary. We have talked about stationarity means the statistical properties of random process do not change with time. Widely since stationarity is common assumed from the real world signals, statistical independence ensures there is no dependency between signal samples. These concepts are virtual in noise modeling, spectral analysis, signal protection, and filter design, whereas there are applications and references. They are have to check it out like noise modeling in communication system, power spectral analysis, and signal protection and filtering, stochastic modeling in control systems, where references like um, waveform backgrounds and communication systems in a stochastic process. Thank you for everyone.